Seems a little twisted, but maybe not. All right, well, we still have the replacement thing here. So do you enjoy square root day? Yesterday was square root day. 5th of May 25, 5 times 5, 25. They say it only occurs 3 times a century or something. Very funny. Okay, so so this is, oh, another one, yeah. So this is the culmination of our symmetric encryption journey, which is the primitive that kind of puts everything together. It's called authenticated encryption. So we're still looking at this basic question of two parties wanting to communicate securely over a network that's insecure or a communication medium. So your adversary is in the middle, and Alice wants to send this message to Bob. And we've looked at two goals. First one is data privacy, which means that the adversary shouldn't figure out the content of what's sent. And we gave symmetric encryption as the primitive to do that, and we gave security definitions for it and schemes and so forth. And then we turned to look at data authenticity, where the goal is that the receiver should be convinced that the message they received was actually sent by Alice, not someone else, and wasn't changed along the way. And for that we gave a different primitive called message authentication codes, and it also came with its security goal, unforgeability under chosen message attack. But these have been considered separately in the sense that when we looked at privacy here, we didn't care about authenticity, and here when we provided authenticity, we didn't care about the privacy part. So naturally though, in practice we often want the two together, and that's what we call authenticated encryption. So there's tons of natural examples. Probably the most central is just that that's what TLS does. So pretty much everything you send nowadays is done through authenticated encryption on the TLS channel. But here's another one where suppose you're considering again a medical information security application. So for medical information we want privacy because medical data is sensitive, but we also want authenticity because if data is stored and being changed or modified, then you want to make sure that those changes are authorized and so forth. So just to say you want both properties, and that's called authenticated encryption. So before we get into the technical part, it may be worth giving a sense that this is very much out there, and people talk about it a lot and build a lot of things. So here, for example, is a blog by a well-known security researcher, and it's called How to Choose an Authenticated Encryption Mode. And it doesn't mince words. He says, I like to complain, and he talks about dumb crypto standards. And how does that happen, or what's the point, is that he says people are using things like CBC mode encryption. And we studied that, and we said it was a good IND-CPA scheme, and that's fine. But the problem is it's unauthenticated, and that gives rise to lots of failures. And so his point is that we should always use authenticated encryption, and he's upset that there's actually pushback against that. And so then he goes into why we should use authenticated encryption, what it is, and so forth. And this is the currently world's most popular authenticated encryption scheme. It's the government standard for Galois counter mode, and that's what your computers and laptops and so forth and phones are implementing and using over TLS. So, so that just to make sure that it's clear that people do want this stuff. Okay, so since it's a new primitive, we kind of start in our usual way. So we'll need a syntax, and then we'll need security definitions. So syntax, remember, means if I want to give you a scheme, then what do I have to give you to specify it? And here the answer is simple. Syntactically, this is no different from symmetric encryption. So all I have to give you is this tuple of 3 algorithms: key generation, encryption, and decryption. And they work exactly as in a symmetric encryption scheme. So the difference isn't there. So now we turn to security. And even there, half of it is known in the sense that there's 2 requirements, privacy and authenticity. But the first one is captured by what we've done before. It's what we called IND-CPA. So this is mostly a familiar object. But for authenticity, we have to give a new definition and formalism. So whenever we talk about authenticated encryption, the idea is it's meeting both of these requirements together. Okay, so so a little more of kind of summarizing what was said, for example, in that blog post, is that early on people did think that you could just use things like CBC and counter, which gave you privacy alone, but they had many failures, and after a while they came to see that the reason this was happening was lack of authenticity. And by now that understanding has grown to the point where authenticated encryption is the default. So if you're going to implement something, you would expect to be implementing just that. And so it's kind of the central primitive in cryptography. And in the end, pretty much everything else we've studied is just going to be leveraged to create this primitive. So it's rarely the case that we use something like IND-CPA just in its own right. Rather, we build it into AE schemes. But it's still an evolving area. There are lots of schemes, different security attributes, different performance, and even new research emerging and changing this area. So, so this is just to recall, since the syntax hasn't changed, but it's a while since we studied symmetric encryption, that what a scheme looks like is there's a key generation algorithm, takes no inputs and returns a key, and this indicates the algorithm is randomized, and usually it'll just pick a random key of some length, for example for AES or some block cipher. Encryption will take the key and the message and give you a ciphertext, and an important element that we saw about this is that the encryption algorithm can be randomized and actually has to be for IND-CPA. So we would expect that to be true. And again, that's what this $sign means. Decryption is deterministic. In the symmetric case, you're given the same key as used for encryption, and you're given the ciphertext, and you have to recover a message. Now, for privacy, we were really only concerned with reversing encryption as being the role of decryption. But when we come to authenticity, decryption also matters from the security perspective. And in particular, it's now very important that it might sometimes reject. And rejection is formalized by saying you return this symbol called bot, and that says I failed to decrypt. And authenticity will center really around when this happens. So here I'm just recalling the privacy attributes. So nothing new here, but since we haven't seen it for a while, remember that IND-CPA gives you these 2 games, left and right, and they have the same interface for the adversary, meaning they export an oracle called left or right, and the adversary calls on 2 equal length messages, and the only difference between the games is here the left one is encrypted, here the right one. The encryption is done with this encryption algorithm of the scheme. Your adversary gets back the ciphertext, and then it outputs a bit saying, I think I'm in the left world, or I think I'm in the right world. The key under which this happens is chosen inside the game and is hidden, so your adversary doesn't see it directly. And it can make lots of queries to this oracle, and replies are consistent, either always left here or always right here. So eventually it outputs this guess, and we define its advantage as the difference in the probabilities of its saying 1 in the right game, where the guess would be correct, and the left game where the guess would be wrong. And the larger this is, the better the adversary does. Okay, so the new thing now is we want to talk about integrity. And here we see the adversary's goal as targeting the receiver. And what it wants to do is get the receiver to accept a ciphertext, even though that ciphertext is non-authentic, meaning the sender never created it. The sender never encrypted anything that gave rise to that ciphertext. In fact, your adversary created it. And if then the receiver accepts, then we have an integrity or authenticity violation. And that's what we attempt to formalize through this goal, which is called integrity of ciphertexts. So we'll develop that slowly, first some intuitive approach and then go to games. So the setup, as usual, is in symmetric crypto, is our adversary doesn't have the key. However, it can see ciphertexts which have been created under that hidden key, because that's a natural capability. You're sitting on the interface between the two parties, so you can see what Alice sends. Those ciphertexts have been created with the known encryption algorithm, but under this hidden key. And messages, we will assume, are actually known to the adversary. Why do we assume that? Just because it makes the encryption, the security notion stronger. So after having seen all that, the adversary steps back and says, okay, that's fine from the sender. My goal is to go to the receiver, give it a ciphertext, and make it accept. So the adversary now concocts its own ciphertext and hands it to the receiver. What does the receiver do? It will try to decrypt. We have the known decryption algorithm, and it'll use the same key as here, which our adversary didn't know. And the only thing that matters to us for authenticity is whether or not decryption rejects. So decryption can output one of two things. One is a string, which is a message, and the other is this symbol saying, I'm rejecting. And to win, all that the adversary has to do is ensure that decryption does not reject. So this is not equal to this bot symbol. In other words, it returns some message. Right? And that's kind of the key point. Any message which decryption returns classifies as a success for the adversary, because the receiver thought some data is present in this ciphertext that was sent by Alice. Now there's a caveat here which says that a simple way for the adversary to win is to take, for example, C1 and send it to the receiver. And of course, in that case, it would decrypt to M1 and not to bot. But that isn't really a win for the adversary, because that was a legitimate, authentic ciphertext. So we ruled that out. We said this ciphertext is not allowed to be anything in this list. And once you do that, we have something non-trivial. Okay, so any thoughts at that level, or should we go on to? Okay, so we're going to formalize this via a game, as usual, called integrity of ciphertext. And as usual, it'll strengthen the informal version a little bit. For example, our adversary not only sees ciphertext and even knows messages, but it may even pick the messages itself. And when it goes to the receiver, it can try multiple times. It'll have many attempts at submitting ciphertext. So in that sense, it's a little bit like a MAC definition. So the model indeed is something like UFCMA, but the difference is that we have as object of consideration an encryption scheme, not a family of functions. Okay, so just for succinctness, I'll let this denote the AND of Boolean statements. Okay, so here's the game. We fixed our scheme. We called it AE with its 3 algorithms. As usual, initialize will pick a random key by running this algorithm and just keep it and freeze it in the game. It's not directly given to the adversary. The next thing we look at is, how would an adversary win? Well, it has to call this procedure or oracle with some ciphertext of its choice. Now, the verify game procedure will decrypt that ciphertext using this key. The adversary may not know ahead of time what will come out because it doesn't know the key, but it's hoping that this will be a message, a string, and not the bot symbol. And that's what the game checks. So if what comes out is different from this rejection symbol, that's all it takes. At that point, we set this flag to true, and the game will return it, and we're saying our adversary has won. So again, very simple way to win. All you have to do is somehow manage to ensure that decryption creates a string that's not the reject symbol. Okay, but now the other side of the coin is the adversary has some help, which is it can learn things about the key through this oracle, which mimics or stands for the sender. So what happens there is you pass in a message, and this thing will give you back an encryption of it. So how does it create that? Well, it knows the key and it knows the encryption algorithm. So it runs those on the message to get a ciphertext. The randomization is whatever E describes. And that same ciphertext is now given back to the adversary. So through this process, our adversary learns how to at least what form valid ciphertext look like, and then it'll try to create its own forgeries. And the final element we have is that if you leave it at that, it's a little too easy to win, because what the adversary can do is call this, get some C, and then just pass that C into here. And then it will decrypt to the same M that was here, and that will not be bought, and that would have set win to true. So we rule that out by here saying that any ciphertext that was created through this call is stored in this set S. And over here, if what you call with is in that set, you will not set win to true. So to set win to true, it must be the case that the ciphertext is not in the set, in addition to the message being a string. Okay, and then you have an advantage. In this case, just one game, not a difference. So we just look at the probability the game running with the adversary returns true. Okay, so that's kind of the main definition for the chapter that we'll play with. So as usual, this is probably the central thing. So any thoughts, issues, questions about that? That's good. Okay. So, so now this is, again, just to recall that we saw these two definitions, and what we're now interested in is getting both of them together. So let's now start looking at schemes and see how well they do, and thereby build up some intuition about integrity. So first off, we know that we need a scheme that has privacy, because if there are two requirements and we need both, it's better to start at least with something which has this and then consider whether this is true. And we had many examples of schemes that do provide privacy, and one of them was cipher block chaining. So remember, this is what it looks like. There's a block cipher, normal font E being used here. There's a random initial vector that gets added to the first message block, pushed through the block cipher with the key, chaining, etc., etc. There's a decryption algorithm which uses E inverse, takes the ciphertext back to here and adds in the prior block here to get the message. And so that would be a good candidate for authenticated encryption. So a natural starting point then is to say, does this, happily for us, already provide the security we want from an integrity perspective? Is it INT-CTEX secure? So what do you think? And the hint is that the details of the scheme are largely irrelevant to the answer. There's a very basic reason the answer is what it is. And exactly how the scheme works is not going to be the issue. You don't have to look at very closely at it and try to find some problem. But anything jump out as whether or not this has integrity? So remember, what it means is that, is it possible for the adversary to create a ciphertext which it would query here, which when decrypted would result in something that's not the bot symbol? Okay? So all you have to do is not have the bot symbol emerge on the decryption. So as an attacker, you want to create a ciphertext, then it'll get decrypted under a hidden key, and as long as the result is not this funny symbol, you win. Okay? Yeah? Yeah, the ciphertext, yeah, you want to create some C and then pass it through here and make sure you don't get bought. Yeah.
So that means there's several valid ciphertexts being spit out in between C0 and CM, correct?
So the ciphertext is the whole thing. So this whole thing is one ciphertext.
Right. But I mean, you could use, like, as an adversary, C1 or C2.
Yeah, you could, yeah. Okay, so that's a start, yeah. So how would you, yeah?
For every cryptic message, the decryption algorithm works.
Yeah.
Because
Yeah, exactly. It's good. So that's the point. It's very simple, right? So this says you want the adversary wins as long as the output is not this symbol, right? But look at this algorithm. Does it ever return that symbol? Well, then you're done. You can put anything you want into there and something will come out and it's not that symbol. So that's all it is. So pass in whatever you want, right? Any string, and it has some valid decryption, and so you violated integrity. So the first thing we learned from that is we had better sometimes reject. So now for the details, if you have to write this on a quiz or something, you have to write an adversary that obeys the rules of the game. So the way that happens is it'll have to pick a ciphertext that you can pick many different ways. I happen to pick a 3-block thing at random, and then you just call verify. Verify just takes that ciphertext as input, and since when we run it through here, it will return something. I don't know what that thing will be. All I care about is it's not bought. Then we get an integrity violation. And so at least we have this little understanding now. You have better see rejections happening somewhere. So people thought then next that we can make this happen by what's called redundancy addition. So what they say is that we will add some kind of padding or redundancy to the message and check that it's present on decryption. So here's an illustration of that, continuing with CBC encryption, since we started with that anyway. So here we have a CBC up to here, a normal CBC encryption of a message. And the new idea is that we will pick some kind of redundancy function. This could be very simple. It could just be something that always outputs the constant n zeros. It could be a little more complex, like you give it a bunch of blocks, it XORs them. There are other things in the literature, and you could even be fancy and use something like a cryptographic hash function. So now the recipe for encryption is that you take your message and then you apply this hash function. It's a public hash function and anyone can apply it. And you let that be an additional last block of your data. So now you think of your data as having been extended by this one block, and that's what you actually encrypt. So your ciphertext now is 2 blocks longer than the original plain text. There are m blocks here and m plus 2 over here. And finally, what's the point of this? Well, decryption will check that it's present. Otherwise, it will return bot. So this scheme was proposed and used and is a nice illustration of how to get authenticity. So we'll look at this in a little more detail. So what I did here is I actually wrote down the algorithms in detail so that we go beyond the picture a bit. So there's a bunch of moving parts. There's our block cipher E, that's the thing inside here. There's our function H, which is the one used over here, and those are both public. And finally, I will just let SE stand for our well-known CBC encryption scheme. But here I'll denote its encryption and decryption algorithms with a prime, because I want to define new ones. So once I have that, this new scheme can be written like this. When you give it a key and message, its encryption algorithm will first, as usual, break the message into blocks, and then add this extra block as the last one. So this is the hash of the original message. Finally, it will run CBC encryption, which is this, on that whole m+1 block string. From the point of view of CBC, this whole thing is the message, and whatever ciphertext you get there is returned. So that's just this picture detailed. Okay, so but now we do want to look carefully at decryption, because that's where we're going to put in some checks. So decryption gets a ciphertext which is supposed to be have been created like this. So since it knows that this C was created using CBC encryption, its first step is to do CBC decryption. So when it does that, it gets what should be up here. So we're now at that stage. However, from the point of view of decryption, you're just parsing what you get out. So you write it as M blocks and as additional block, which we'll just call T. Then what the decryption algorithm does is it itself computes the hash function on this part and checks if T was correct. So it's saying, when I decrypt, I get something here, some candidate value of H of M, but is it really H of M? And if they match up, then it says, okay, I return the message. And otherwise, and now this is the part that's supposed to give you integrity, it says, no, if it doesn't match up, I'm going to reject. So this was the idea, and this was a well-used idea, and it has some good intuition behind it. So why would we think it works? Because we think of the adversary, like in our last example, as concocting this entire ciphertext by itself. So in our last attack, we, for example, just picked it at random. So if an adversary does something like that, well, when you go through CBC decryption, pretty much you're just going to have random stuff up here, including up here. So it's very unlikely that what you will produce here will actually by chance match the hash of what's here. And that's our, at least the hope in terms of security. So this was a scheme that was employed in, for example, some wireless standards. But after a little bit of thought, people saw that it fundamentally doesn't work. So we're going to give an attack on it. But one thing that's interesting about the attack is that it's very generic. It's not going to care in particular what hash function was used. No matter what the hash function is, it'll still break the scheme. So what's the idea? Our adversary will begin, let's say, with some one block message. And then it will itself compute the hash of that message. This hash function is public. And think of that as the second block of this message. So now you have a two-block message, and you can pass it into our encryption oracle and get the ciphertext. From the point of view of the encryption scheme, all this is just the message, it's data. The fact that the second block happens to be the hash of the first is not something it knows or cares about or checks. It just has its own process of encrypting. So how does that process go? It says, this is the data. I'm going to hash the data, make that the third block, and run CBC. So when you do that, you get at the top here this 3-block thing, and here these 4 blocks coming from CBC. So when the adversary calls the encryption oracle, it gets back this 4-block thing. Okay, so but now what the adversary notices is that all it has to do to get a valid forgery is to ignore the last block over here. If you just look at these 3 blocks, they work, right? Why? Because the last block is indeed the hash of whatever came before, and everything else is valid CBC encryption. So all you have to do is call verify on this truncated ciphertext, and you're done. So, okay, so that's what it looks like. Yeah? So that's the choice that was made in this paradigm. You could change it, and if you do, you'll improve it. That'll fix things basically. But when people did this historically, they didn't think that was necessary, and they were wrong. Yeah. Okay. Anything else? Okay. So this is the history behind it. This type of scheme was used in early versions of the secure wireless protocols, the things that you use to access your internet routers, like at home or here, and they do encryption. And due to this, there were some problems. Okay, so far what we've done is we've developed some intuition about authenticity, but we haven't actually found anything that works. So now we're going to move towards doing that. And the approach we take is quite natural. We don't try to go back to scratch and build something completely new, but we remember that authenticated encryption has 2 parts, privacy and authenticity. We already know how to achieve the privacy, and we have multiple choices of symmetric encryption schemes that do that. For example, CBC, maybe with the AES block cipher, counter mode with the same. So that part we're good on. But we also remember that we had MACs, or even better, PRFs, which we used to develop message authentication codes and were a way of providing authenticity. So the natural idea is just combine these 2 in the right way and you should be done. We have many choices of this, for example, HMAC, CMAC, encrypted CBC MAC. So the question is, how do you combine them? And that's what we're going to look at through a method we'll call generic composition. So again, maybe it's good to give some background and motivation here, but you can see that this is a well-known thing and people study it and talk about it. This is like a Stack Exchange post where someone wanted to understand this. So they say here, data when it's encrypted must also be protected with a MAC. They talk of some schemes, but then they look at 2 different types, MAC then encrypt or encrypt then MAC, and they say which is better. So in fact, they look at 3 things and they ask. And in the end, that's exactly what we'll end up studying and answering. So pretty much the slides will answer this person's question. And this goes on, so here, for example, are people who are discussing, again, those 2 choices, and they give you the different mechanisms and what works and doesn't and so forth. Okay, so let's start building up how we do this composition stuff. So we're trying to build an authenticated encryption scheme. And again, there's a bunch of moving parts because we're starting from a symmetric encryption scheme that's given, like counter mode or CBC, and a given pseudorandom function. We'll call it f, and we have many examples. And what I want to create is a new encryption scheme which also has integrity. And that I'll call AE, and its algorithms will be denoted like this. Since this scheme also has key generation, encryption, and decryption algorithms, I will put primes on them. So again, there are quite a lot of moving parts, 3 algorithms here, and a 4th one here to start with, and 3 more we're trying to design. Okay, so in designing this, let's just do it step by step. So we'll start with saying how key generation works. And the answer is that since there are 2 things here, encryption and a MAC, our key generation here will just give us keys for each of them. So this algorithm will first run this one, and get a key which it can use for SE. So that's our encryption key, K sub E. Now it also wants a key for the MAC or PRF, and this PRF we're going to write as taking k-bit keys, arbitrary length messages, and outputs of n bits. So since keys here are k bits, it grabs a random k-bit string and calls it K sub M for MAC. And so this thing here is the key for our new encryption scheme. That gives it the ability to do both encryption and MAC using these two primitives. And this is going to be fixed for everything we study in generic composition. So we'll always be appealing to these two keys. Okay, so now we look at different ways to put these together. And this is where the subtleties enter, because once you're handed these two primitives, you might think it's very easy or obvious how to glue them together, but in fact you have a few choices, and largely these choices are expressed in ordering. Which do you do first? This is encrypt. This actually is in parallel, encrypt and MAC together, most natural thing. This is first MAC and then encrypt, and this is first encrypt and then MAC. And not only are these considered theoretically, but they're used. For example, SSH is a secure file transfer protocol which used this at some point. Early versions of TLS used this. Later ones use GCM, so maybe not so relevant. And IPsec at some point used this. So, and now we'll study them, and this is kind of the answer to the stack exchange question. So I'm going to take a bit of a different approach here than usual, in the sense that we'll just kind of eyeball these methods and check for intuitively for vulnerabilities or security. But in order to do that, there's maybe a few things that should be clarified about what we mean by this composition method being secure. So first off, what we'll see is we'll consider both goals in privacy, IND-CPA, and integrity. And then for each, we'll ask, does the scheme work? And if you answer yes, what you're saying is that no matter what choice of the base primitives I make, as long as they satisfy the security conditions for which they were defined, my new scheme works. So all I need is this is IND-CPA, this is a PRF, and authenticated encryption will have whichever of these two properties we're looking at. And no means that it doesn't work, but that doesn't have to be true for all choices of the base primitives. As long as you have a counterexample, meaning one choice of SE and one choice of F, which result in this failing, then we are going to declare the composition method to fail. So that'll get exemplified a bit as we go on. Okay, so now let's start writing down these methods, and they're pretty intuitive. So let's see if we can start with the encrypt and MAC. So here my goal is that I want to get both privacy and integrity, but I already know that I have these algorithms, E prime, which can give me privacy, and I have the ability through F to create tags which give authenticity. So it should be pretty simple. So what do? I have here a key which enables both encryption and MAC. So I take my message and I encrypt it with the base scheme and get a ciphertext. And this ciphertext, I know actually, is going to provide privacy of the message, because I know that this E prime works. Okay, but that doesn't give the authenticity. So let's add that on. I use this F function, which is a MAC, under its key on the message and get a tag. And I know that this does provide integrity, because we studied that these kinds of functions are good MACs. And now I output this ciphertext together with the tag. And I want to see this as providing these two properties for this encryption scheme E over here. So that's how encryption works, but as we've seen before, we do need to look carefully at decryption. In particular, if it never rejects, we will never have integrity. So let's write down how decryption would work. So it gets a ciphertext that has this kind of form, And the first thing it does, it says, okay, this part comes from this other algorithm, E prime. So I can reverse that. I have the decryption algorithm, I have the corresponding key, I run it on this ciphertext, and I get back the corresponding message. So I now have the data. But I'm not going to directly return it. I'm going to first check that the authenticity is true. So I will compute the MAC, just like here, on the message, and that gives me the correct value of the tag. Now I compare it to what's over here. If they match, then I say, okay, this is authentic, so I will return the message, but otherwise I reject. So that's the scheme, and we'll be looking at this, but the first question is, do the algorithms make sense? The scheme algorithms? Okay, so then let's give it a shot. And like I said, it's just basically guesswork here, because we're not going to prove anything or really try to write attacks even. But intuitively, what about privacy? Do you think, but you do know what IND-CPA is. Remember, it's a strong goal. It has many attributes. For example, you can't detect repeats, right? There are many elements of this goal that have to be considered. So in the understanding of what this goal is, would this scheme provide privacy? Right? So what we're asking there is, you get to see ciphertext like this, and you have to tell, is it a left or right message where it's coming from one of two messages you query to left or right. Or you can look at it, somewhat more intuitively. But so any thoughts? Does this look like it provides privacy? Yeah? It is the same, yeah. We know what? Yeah. So when you say key, so the keys are here, right? Oh, the T, yeah, good. Yeah, that's right. You always return the same T. So that's the problem here, right? So what happens is that when if you twice encrypt the same M, this part is not going to change. And that's immediately an IND-CPA violation, right? So curiously enough, we would say that we would determine that this actually fails to achieve privacy. And what's subtle about that is that this part did achieve privacy. And if we had left it at that, we would have had privacy. But in our attempt to add authenticity, we actually messed up the privacy. Okay, so let's go back. So do people see why this is not a problem, not achieving security? Because this is kind of the intuitive rendering of IND-CPA that you can hopefully get out of the definition. Okay, so again, anything that's a deterministic function of the message present in the ciphertext will violate IND-CPA, because you can tell whether a message has been repeated as encryption. Okay, so actually then we started off rather badly. We can still ask if INT-CTEX holds, and here the answer is a bit more subtle, but it turns out that it actually doesn't hold. And the reason for that is that it's possible for some choices of E prime to take this ciphertext and modify it so that when you go here in the verify oracle, it will be a new ciphertext. But you modify it in a clever way so that when decryption happens, the message underlying it doesn't actually change, and hence the tag will be correct. And that will result in ctext violations. Right? So it's a little more subtle, because we're not claiming it never works, but that it sometimes doesn't work. Okay, so this was quite bad. We failed on both. So what can we try next? Well, we saw that we created a lack of privacy by the way we did authenticity. So what we'll do now is reverse things by saying, let's first authenticate and then encrypt. So what's the change? We first compute the authentication tag on the message, as T using our F with this key. And now when I encrypt, I don't encrypt just the message, but I actually encrypt the tag as well. Because the idea is now I'll protect privacy of the tag in addition to privacy of the message. And that's the ciphertext I return over here. Okay, so again, we do have to consider how decryption works. So what would it do? Well, first off, it knows that this C was created like this. So it will reverse this E prime and through the D prime with the same key, run on the ciphertext, and that'll give back something that should have this form. But at this point, it doesn't know whether this T is really equal to F of M. So it checks that. It now says, I have the message, I can compute this function since I have the key, and I'll check the tag. And again, as before, if the tag is valid, you return the message and otherwise reject. Okay, so that's our new attempt. So again, does the scheme make sense before we start thinking about it? Or okay, so now what do you think? Just guesswork basically, but now do you think you have privacy? Okay, Richard, why is that?
Because the exploit we had before to like make T deterministic no longer applies because we're encrypting it. And since we're only given the ciphertext from the encryption, you have to like decrypt it before you could do anything with that.
Yeah, right. So the thing is that what you're getting here is a ciphertext under E prime, but we know that E prime is secure, and there's no other information out there. So the expectation is that it'll work. And indeed, that's what happens. So we made progress now. Now, again, it's a little subtle, but unfortunately, we did not remove the prior problem with integrity. And the same kind of attack continues to hold in the sense that if by chance you could create a ciphertext given some C, it could be possible to create a different C which decrypts to the exact same thing. And since the check here is only on what emerges from decryption, that would fool the anti-C text game. Okay, so but there's one more thing we could try, which is we could change the order in the other direction to first encrypt and then authenticate. So what that means is that in this case, I would go back actually to the first thing where I do encrypt just the message under the old scheme with the corresponding key, and I get this ciphertext. Now, in the first encrypt and MAC case, what we did is we applied the F to the message to get the tag. But that wasn't working, so I won't do that. Instead, I'll apply it to this ciphertext. So I will authenticate the ciphertext here. And then, as in the first case, I'll return both those things. Okay, so that's the encryption part. So what does decryption do? Well, again, it starts by saying, I have this, and it's supposed to look like this. If that's the case, this has been created from this encryption. So I'll just start by reversing that. I use the decryption algorithm of that scheme, run it on the first part of the ciphertext here, and get a candidate message. But before outputting that, I'll check the tag. And I know that here the tag is computed on the first part of the ciphertext, C prime. So I can run F also, get the correct one, and check. And if they match, I return M, otherwise reject. Okay, so same things again. So does the scheme make sense? Okay, so let's try again. So what about privacy this time? I mean, just a guess, right? Does it look like you've achieved privacy? I see lots of yeses. So anyone want to say why? It's a good guess, yeah?
I would say yes, because the ciphertext part of C prime has that security, and then T is no longer irredeterministic because C prime is changing.
Yeah, so basically, once this has privacy, if you put stuff on top of it, it's not going to change it. It's just, it's computation done on top of something that already has privacy. So intuitively, yeah, it's going to work. And it turns out that now the other one will work as well. And that we don't, don't have to detail that. So the conclusion from all this is we found something that works, right? So this is kind of the punchline, is now we've solved the authenticated encryption problem. We have a method that works, and moreover, it's not just one method, but a whole collection, because we have many choices of this E prime, many choices of F, and we suddenly have a whole slew of ways to build authenticated encryption. Okay, so then there's some details about this. One is just that we used a long key, which was parsed as two separate keys, one for encryption, one for MAC, inside our authenticated encryption scheme. Sometimes people don't like storing bigger keys, so what they do is they just derive them from a single, say, 128-bit key. And there's simple ways to do that. For example, run a block cipher like AES on a short key on a couple of constant values, and their outputs you can use as subkeys for the two parts, and that turns out to work. But a caveat here to be careful about is to not do this naively. Sometimes what people do is they say, if I'm using CBC encryption and CBC MAC, why don't I just share the key across them? And that turns out to be difficult. So that may lead to problems. Okay, so this is a exercise. So there's not much more to say here. So just that this is a popular primitive, but it's evolved. So nowadays, if you look at authenticated encryption, it's not having the randomized form we talked about, but it uses an additional input called a nonce. So in particular, if you look at this GCM scheme in the standard that I pulled up, that's the type of scheme it is. It takes this input called a nonce. But if you think of the nonce as random, you kind of get back to our case. The next thing that happened is that people got really interested in speed. And although encrypt and MAC works, it has a slowdown from doing both the encryption and the MAC operations. And people found that you can build schemes that are pretty much the same performance as plain privacy modes. So pretty much as fast as plain counter mode, it's actually possible to get authenticity as well, but not through generic composition. You do some clever stuff. And there's a bunch of schemes like this. There was so much interest in this that there was an entire competition called Caesar, which put out a call for people to submit designs to build new authenticated encryption schemes, and then there were winners of that competition and so forth. And finally, on the research front, there's been an evolving sequence of goals and security attributes. So people started realizing there's this additional thing you need called committing security, and they started building schemes meeting that. They started searching for new kinds of efficiency properties and so forth. And all this is still ongoing. If you go to crypto conferences, you see papers with all this type of stuff. Okay, so that's actually all I had. This was a nice short chapter, so happy to take any thoughts or anything, or we'll talk. But otherwise, I don't want to start the number theory now, but like I said, I'm out of town for 3 lectures, and I put that on the videos. I would have preferred to do it in person, because just a warning is number theory is deceptively tricky. It's the kind of thing where everything by itself is simple enough, but then when you put it together, you can get confused. So it's good to kind of work through in a nice sequential manner and check it out. Okay, so anything further? Okay, yes, we'll end early today then.